Now we're thinking about oscillations. As we'll see later on, oscillations cause all wave phenomena. And when we start to talk about oscillations, the simple system that we use as a model for any kind of oscillating system is just a mass connected to a spring. Uh, Nothing really all that interesting in itself about a mass connected to a spring, but it's a useful model because any oscillating system, all oscillating systems will be similar to this in many significant ways. So just imagine this. First of all, remember the spring force. Imagine that you've got a mass just sitting connected to a horizontal spring. The mass is free to move left to right, and one end of the spring is fixed, connected to a wall or something, and the mass slides back and forth along some kind of a very low friction surface, so that really the only force, um, the net force on the mass is supplied entirely by the force that comes from a stretched or compressed spring. Start out here with the spring just at its normal, unstretched, unsqueezed length. So in that state, the spring is applying no force to the mass. So the spring force is zero, the net force is zero, because the spring force really amounts to the net force in this case. Now, imagine stretching the spring by pulling the mass to the right. What have we done here? We've moved, there's now a displacement of the mass away from this point, which was the equilibrium point. Remember, equilibrium means no net force. Right? When the mass sits here, it feels no net force because the spring force is zero right there. But of course, when you stretch the spring being an elastic object, is going to try to snap back to its original shorter length, and as it tries to snap back, it pulls to the left on the mass. So you displace the mass one way, it feels a pulling force the other way from the spring. And that's really what this equation for the spring force tells you. Whenever you have displacement, you have a spring force, and the spring force points opposite to the displacement. That's what this minus sign means. In this case, the displacement was to the right, and the spring force is now pulling back to the left. One other thing you notice is that the more displacement you have, the stronger the spring force is. So in this case, we've pulled the mass to the right, so now there's a spring force to the right. That spring force is supplying the net force. And when there's net force to the left, there is acceleration to the left. So as soon as you let go of the mass, it'll start to accelerate. It'll start to pick up velocity towards the left. And anytime you're moving to the left, but acceleration is also to the left, remember that whenever velocity and acceleration point in the same direction, that always corresponds to speeding up. So when you've pulled the mass to the side and then let go, it's going to speed up as it heads back to the equilibrium position. So by the time it gets to the equilibrium position, it'll have a higher speed than it's ever had before. And now, here's the mass at equilibrium. It's gained velocity. But of course, now it's back at equilibrium. It's not displaced away from equilibrium. So that means there's displacement away from equilibrium is 0, so spring force is 0, so net force is 0. At that moment, the acceleration is 0, but it still has velocity. So even though there's 0 net force, inertia will keep the thing moving to the left. So a short time later, it'll be over there to the left of the equilibrium position. That means that now there's a displacement to the left away from equilibrium. And that the spring is squeezed. And being an elastic object, the squeezed spring is going to try to snap back to its original longer length. In trying to expand back to its original longer length, it's going to push to the right on this mass. So now, because there is displacement away from equilibrium, there is spring force. Right? That's not 0, so that's not 0. And this displacement was to the left, so the spring force must point in the opposite direction. The spring force pushes to the right. That spring force, remember, is what amounts to the net force on the mass in this particular case. So net force to the right, acceleration always points in the same direction as net force. And as we know, and remember, the block is still moving to the left. It still has velocity to the left. Whenever you have velocity one way and acceleration the opposite way, the thing slows down. And it'll slow down until eventually it comes to a stop. When it comes to a stop, it's still displaced away from equilibrium, so the spring is still squeezed. So the spring is still going to try to snap back to its original longer length, so the spring is still pushing to the right on the mass. There's still a displacement that points to the left, so there's still a spring force that points the opposite way, points to the right. So displacement to the left. So spring force, which means to the right, which means net force to the right. Which means acceleration to the right. Even though all that time, from the moment the mass was at equilibrium until the moment the mass gets over here, it's been moving this way, but it's been feeling a net force pushing backwards, so it's been slowing down. Now, of course, it's slowed down to a stop. There's 0 velocity at that point, but there's still net force and acceleration at that moment. And since there's still net force and acceleration, the velocity doesn't stay 0, just has a value of 0 for 1 instant. So let's see what we've got here. This mass has gone through 1/2 cycle of an oscillation. It started out way over on the right at 0 speed, and then you let go, and it moves through equilibrium, and then and then goes as far as it's going to go on the left-hand side, and then comes to a stop again. Notice both here, when the mass was displaced to the right of equilibrium, the net force was to the left. In other words, the net force was pointing back towards equilibrium. Now here, when the mass is displaced to the left, the net force is pointing to the right. In other words, the net force is pointing back towards equilibrium. That's the way it always works in an oscillation. Oscillation will happen because the net force on the object is always pointing back towards equilibrium. Whenever the object is displaced away from equilibrium, the net force will always be trying to pull it back towards equilibrium. The net force always points towards equilibrium. So now let's, what happens after this? The mass has, for one instant, come to a stop, but it still feels velocity and acceleration this way, so it starts to move this way. So it starts to move that way. Now it has velocity to the right as it approaches the equilibrium position, but it's still displaced away from equilibrium, which means this spring is still squeezed, so it's still trying to stretch back to its original length, so it's still pushing towards the right on the mass. The spring force always points opposite to the displacement, so the spring force here is always pointing opposite to the displacement, so the net force is pointing opposite to the displacement, because in this case the spring force really just amounts to nothing but the net force. Net force to the right means acceleration to the right, and anytime you've got velocity and acceleration pointing the same way, they're both pointing to the right in this case, the mass is going to speed up. Once again, we see the net force pointing towards equilibrium, trying to push the mass back towards equilibrium. And just as we saw in the first part of this cycle, way back when the mass was on the right and moving towards equilibrium, back then, as the mass moved towards equilibrium, it had a net force pulling it back towards equilibrium, so it was speeding up. Same kind of thing here. The mass is moving back towards equilibrium, and it feels a net force that points toward equilibrium, so it speeds up again, until finally it gets back to equilibrium. And it's no longer displaced away from equilibrium. Zero displacement. So the spring force is zero, which means the net force is zero, which means zero acceleration at that one point. But of course it has velocity at that point. It's been gaining velocity all the time that it was approaching equilibrium. So since it has velocity here, its inertia will keep it going with that same velocity. It won't stop here, it'll overshoot, and it'll start to move to the right. It'll continue to move to the right. Now it'll be to the right of equilibrium. And what happens then? There's equilibrium. Now the mass is here, displaced to the right of equilibrium. And remember, it's still moving to the right. velocity to the right. But now, since the spring is stretched, it's going to try to snap back to its original shorter length, which means it's going to pull to the left on that mass. The spring force is to the left, which means the net force is to the left, which means acceleration is to the left. And remember, anytime velocity and acceleration point in opposite directions, the mass must slow down. So again, the net force points toward equilibrium. The net force points opposite to the displacement. That net force is trying to undo the displacement and restore the mass to equilibrium position. So now the mass is slowing down. Eventually it slows down all the way to a stop. Zero velocity, but when it comes to a stop, it's displaced away from equilibrium. The spring is stretched by that much, and since there is a displacement away from equilibrium, there is a spring force. Since the spring is stretched, there is a spring force. The spring tries to snap back to its shorter length, so it pulls to the left on the mass. Even though at that instant there is zero velocity, there's still net force, so there is still acceleration to the left, which means the velocity doesn't stay zero. It has that value of zero for just one instant, and then instantly begins to gain rightward velocity. This is the same state that we saw at the very beginning of this process, right after we had pulled the mass to the right and then let go. This is exactly the state that we had back then. So now, right here, the mass is in the same state exactly the same state that it had before, and now it's going to cycle through all of the same situations that I just described here. It'll cycle through all the same situations. That cycle will look exactly like the previous cycle, and then it'll cycle through those same steps again, and then it'll cycle through those same steps again. We have an oscillation. The main idea is that we have an oscillation because the net force on this oscillating mass is a so-called restoring force. And by restoring force, we mean a force that's always pointing towards equilibrium and always pointing opposite to the displacement away from equilibrium. Right? Here, the mass is to the right of equilibrium, so the net force, being a restoring force, is pulling it to the left. Over here, the mass was to the left of equilibrium, so the net force, the restoring force, was pushing it to the right, trying to push it back towards equilibrium. That's the basic pattern that you'll see in oscillation, that you'll see in any kind of an oscillation. And I'll give you a little exercise to work with here on lecture exercise to deal with this, and then in class we'll look at a different kind of oscillation and then make some measurements with the motion detector.